1 Dynamics, example 15. I've drawn a diagram of this situation here. We've got a particle on the table with a mass of 0.4 g. That would have a normal reaction upwards. It's a rough table, so I've drawn a friction against the direction of motion, and the tension in the string will be pulling the object along towards the edge of the table. We've also got a particle hanging off the edge of the table. The tension is holding it up, and it's got a weight of 0.8 acting down. Now we think about particle A to start off with. We know that R would be equal to 0.4 g, and so the friction would be mu R, so that would be 0.2 multiplied by 0.4 g. So the friction is 0.08 g. So we'll keep that for later. First thing we have to do is find the acceleration. Now the whole system would accelerate to the right. And what I'm going to do is I'm going to do F equals ma for both particles. This particle is going to accelerate downwards. This particle is going to accelerate along the table. So if I do it for A to start off with, if I do F equals ma in the direction of motion, we've got tension pulling it forward. We've got friction, which we've just worked out, acting backwards. And that's equal to the mass, which is 0.4, multiplied by the acceleration, which is what we have to find. Do the same thing for particle B. This one's accelerating downwards. So 0.8 g downwards, tension is holding it back, and that would be 0.8 a. Now we've come across a situation like this before, and the easy way to solve it, because you've got a positive t and a negative t, is to add the two equations together. The t's will then cancel out, and you'll have 0.8 g minus 0.08 g, and that would leave us with 0.72 g. On this side, we'd have 1.2 a, and so if you divide by 1.2, we get that a is 0.6 g. So I'll just leave it like that. I'll leave it exact. The second thing we're asked to find out is the time it takes for B to reach the ground. Now, we know that it's 0.5 metres above the ground currently, so that's the distance it has to move. We know that when the system is released, it's released from rest, so the initial speed is 0. We know the acceleration is 0.6 g, and we're asked to find time. So in this question, I would use S equals ut plus a half at squared. So that tells us that 0.5 is equal to 0 plus a half a t squared. Solving that equation, remembering to square root at the end because that's t squared, gives you a value of around 0.412. The final part of the question asks us the total distance travelled by A before it comes to rest. Now there's two sections to this motion. For the first section, the particle's being dragged along the table because it's fastened to B. But once B hits the ground, this string will go slack and the particle on the table will have nothing pulling it forwards. It'll be moving along, friction will start to slow it down, and eventually it will come to rest, hopefully before it falls off the edge of the table. So the first thing we need to do is find out what happens when this string goes slack. And if we think about particle B, it starts off with a speed of 0. It's got an acceleration of 0.6 g. We know that when it hits the ground, it's gone for a time of around about 0.412 seconds. I'll use the full value there for my calculator. So we can find out the speed it's going at when it hits the ground. So v equals u plus at. So v will be 0 plus 0.6 g multiplied by this time, and that works out to be 2.424. Keep that value in your calculator. So that's the speed that B's going at when it hits the ground. Now the reason I've worked that out is because we can then work out the speed that A's going at. And because the string was taut at the point when it hit the ground, A would be going at the same speed. So we think about what's happening now to particle A. It's travelling along with this particular speed, and the only force acting on it is friction, slowing it down. So if we think about F equals ma for this particle, once the string's gone slack, the only thing acting on it is a negative force, that friction that we worked out earlier. The mass is 0.4, so we can work out the acceleration it's going at now. Divide by 0.4 and you get minus 0.2 g. That's the current acceleration. So for particle A in this second phase of motion, the acceleration is negative. We know that it's initially u travelling at 2.424. That's the final speed when B hit the ground. That's the speed that A is travelling at the beginning of this second phase of motion. And we know that we want it to come to rest. So what distance has it gone? Well, if we use v squared equals u squared plus 2as, v is 0, u is this value here that we've got in our calculators, and then we've got minus 0.2 g for the acceleration, and s is what we want to know. Now, if you go ahead and solve that equation, s actually works out to be 1.5 meters. Looking back at the question said find the total distance travelled by A before it comes to rest. So it had actually already travelled a little bit of a distance along the table before the string went slack. Now, how far had it gone along the table? Well, it had gone the same distance along the table that this particle had gone to the ground. So particle B was half a metre above the ground, so as they moved, this particle would have gone half a metre along the table. So we have half a metre in the first phase, then when the string goes slack, we had another 1.5 metres. So the answer is that it's gone a total of 2 metres.